Hello and welcome back to another video. In this video, we'll be moving on to section 1.3, which is all about the Fundamental Theorem of Calculus. So just to recall, in section 1.1, what we went over was Riemann sums, right? Which remember, Riemann sum was just a fancy word for using rectangles to approximate areas. So we were approximating areas, right, or definite integrals using rectangles. And then in section 1.2, what we did was that we decided we could also not limit ourselves to just rectangles, but use triangles, trapezoids, circles, any known shapes to calculate definite integrals. And then we also learned some properties of definite integrals. So we calculated definite integrals using known shapes. So we were still just interpreting the integral as an area. And we learned properties of integrals. So I'm sure that you'll be so happy to realize that in section 1.3, the fundamental theorem of calculus will establish the relationship between derivatives and antiderivatives and will give way to using integration formulas or the antiderivative formulas in order to calculate integrals more directly. So basically now, going forward, we are abandoning the whole having to graph and having to figure out area formulas in order to determine a definite integral. Okay. It's important to know, like, the fundamental theorem of calculus, which I'm going to abbreviate as FTC, right, is arguably the most important theorem, or one of the most important theorem in calculus. And like I said, it establishes the relationship between differentiation and integration, right, or derivatives and integrals. Okay, so the fundamental theorem of calculus has two parts. So let's write out the entire thing. So suppose that f is a continuous function over the interval a comma b. So what part one says, essentially what part one says is that the derivative of the antiderivative is the function itself, right? Where like the derivative and the antiderivative undo one another. So I'm just going to write the whole technical theorem down first. So if capital F of x, so we use capital F to denote an antiderivative, is equal to the integral from a to x of f of t dt is the antiderivative function giving the area under f of t from a to x, right? So that's how we've been interpreting integrals this whole time. Then f of x is differentiable and its derivative is just lowercase f of x, right? So in other words, the derivative of capital F of x is just lowercase f of x itself, right? So if we take the derivative, remember this notation, d dx is the derivative with respect to x of this integral, we just get the function itself back. So these are pretty much saying, right, these are the same thing, just with different notation, right? And what it's saying is that the derivative of the antiderivative is the function itself, right? So they cancel each other out. Okay. So I just kind of want to go through an example of doing this to show you how it works out, right? Because remember, it's so important that we pay attention to details. So like this only works this nicely when you have these specific bounds. You're going to need the chain rule if you have a bound different than that. So a is just a number and then x is the variable itself. So if it's more complicated than that, you're gonna have to be a little more careful. So let's do a couple examples using part one of the fundamental theorem of calculus, and then I'll go into part two. Use part one of the fundamental theorem of calculus to find the derivative of g of x equaling 1 to x of 1 over t squared plus 1 dt. Okay, so if we notice, right, the bounds here, this is just a number, and this is just x. So when that's the case, you're able to literally just apply this rule, right? So if I want to take the derivative of this function g, since our bounds in this example is just a number 1 and a letter x, right, it meets the formatting of the theorem, right, where a is just a number and x is a variable, different than the variable in here, right? So we have that same exact case, so we're able to easily just apply this theorem, right? So we can just literally say g prime of x, right, that's the derivative of g, is equals to, all we have to do is plug in x, right? If we have the derivative with respect to x of this function in here, which we have some things very similar to this, we just get whatever's in there, but with x instead of t. And that's our answer. And however, what about when we have something other than just a number and an x? That's when things get a little complicated. But before I go there, I'm going to introduce part 2 of the Fundamental Theorem of Calculus. So what part 2 says is, right, we still have the same thing. If f is continuous over the interval a comma b, and f of x is any antiderivative of f of x, then the integral from a to b of lowercase f of x, right, is just the antiderivative evaluated at the upper limit, so b in this case, minus the antiderivative evaluated at the lower limit. So, right, so before we write this, commonly you'll see that what we do is we take the antiderivative, capital F, and then we do this long bar, and then we put a and b, we put the limits of integration there. And that just means like you plug in b first into capital F, and then you plug in a and you subtract them. So I just wanted to show you that notation. It's often used to signify that. Right, so this is notation used to signify to plug in a and b. Right, and find the difference the way we did, right, where we plug in the upper limit first. Right, so it's always the upper limit first and then the lower limit. So that is written in order on purpose. Back into the example that we did before, this allows me to sort of explain it just a little bit more, right? So if I continue with this and I have g of x equals the integral from 1 to x of 1 over t squared plus 1 dt, right? And then suppose that capital G of x is the antiderivative of the integrand, which is 1 over t squared plus 1. Then, right, then we know that g of x, right, what we just learned is if we do this integral, we can just take the antiderivative, right? So we take the antiderivative, which we're calling g of x. Right, so in this case, we integrated with respect to t, so it's still going to be t, but then we evaluate that at 1 and at x, right, which we just learned means that I first plug in the top bound, so I plug in x, and then I plug in 1. Right, so now I have that g of x is equals to capital G of x minus g of 1, but remember, I want to take the derivative. That's what it told me, to find the derivative of g. So I need to find g prime, lowercase g prime. So lowercase g prime is equals to the derivative of capital G of x minus capital G of 1. Right, and remember, we can always do derivatives term by term if we have addition or subtraction. So we can do the derivative of capital G of x minus the derivative of capital G of 1. And remember, g of x is the antiderivative. So if I do the derivative of the antiderivative, what's that? Remember, we just get the function itself back. So the function itself, remember, the function itself is this 1 over t squared plus 1. Right, we said capital G is the antiderivative of this function. So if I take the derivative of this antiderivative, it's going to cancel out the antiderivative and I just get back to this. So the only thing is now we have it in terms of x. So that's why it ends up changing to x values. And then remember, if we plug in a number into a function, what we get out is a number. And then remember, the derivative of some number is just 0. So this just becomes 0. Oh, I erased my 0 on accident. So g prime of x, again, right, is just 1 over x squared plus 1. So that's the final answer for that. Okay, let's just do one more example like that, because I know that like these examples, they're actually really simple, but it takes a little bit getting used to. So remember that the key thing is that if you have a number as your lower bound and you have x as your upper bound and you're finding the derivative of the antiderivative, all you have to do is just change the variable. So we're going to do find the derivative of the integral from x to 4 of the square root of t cubed plus 5 dt. Okay, so, right, you notice we just have a number and an x. However, if we look at our theorem, the x is on top and the number is on the bottom. We have it flipped here, and that's an issue, right? That's an issue because it will change the ordering of this in here. So before we're able to apply the fundamental theorem of calculus, we have to use the property we learned in the last video. So what we're going to do is realize that, oh, this integral here is actually equal to negative 4 to x of square root t cubed plus 5. Remember, we can switch the bounds if we pull out a negative sign. Okay, let me just move this over a little bit. And so now if we want to find the derivative of this side, we can do it by finding the derivative of this, right? So we do the derivative of negative 4x root 2t cubed plus 5 dt. And remember, we can pull out constants out of a derivative. So this becomes negative d dx. And then we have it in the form that we want it, where the lower bound is a number and the upper bound is an x, and then we're taking the derivative with respect to x. So then this just becomes negative root x cubed plus 5, right? So that's the final answer for that one. So hopefully that makes sense. The key thing again with everything is don't overthink it. Use the theorem and apply it, but just make sure that you pay attention to details like the bounds being flipped. Okay. Find the derivative of the integral from 1 to x squared of t squared plus 4 dt. So let's call this function here, let's call this f of t is t squared plus 4, and then suppose that capital F of t is the antiderivative of lowercase f. So then we know that this becomes the derivative of, using part 2 of the fundamental theorem of calculus, we can use the antiderivative of f, which is capital F, evaluated at 1 and at x squared, right? So that becomes, right, we plug in the top bound, which is x squared, and then we subtract and plug in the bottom bound. However, now we have to be careful, right? Because now if you notice closely, what is this? Right, this is a function. Capital F is a function itself, and it has another function, x squared, plugged in. So what does that remind you of? When you have a function and another function, we need the chain rule in order to be able to take the derivative, right? So a function x squared plugged into another function, capital F of x, requires the chain rule. So remember, the chain rule, let's just write it out really quick, just as a brief reminder. Chain rule says that if you're given some function f with some function g plugged inside of it, then the derivative of f of g is the derivative of the outer function with the inner function plugged in with times the derivative of, right, all times the derivative of the inner function. Okay, so that's what we have to use, right? So if we want the derivative of capital F of x squared, right, we have to do the derivative of the outer function, which is the derivative of capital F, whatever that is. Then we plug the inside in, right, and then we have to multiply all of that times the derivative of the inside, which, remember, the derivative of x squared is 2x, right? And then when we move on to do the derivative of capital F of 1, remember, that's just a number. When you plug a number in a function, you get a number out. So the derivative of a number is just 0. right? So this is just f, capital F prime of x squared times 2x. And I like to just put two parentheses to make sure we don't think we're multiplying the x squared by the 2x. No. And then if we do the derivative, right, we're doing the derivative of the antiderivative, so that's just going to become the regular function itself. So that's f of x squared all times 2x. And then what was f? Oh, remember f was, we set it equal to this, t squared plus 4. So we have to plug in, so f of t was t squared plus 4, and we need to plug in x squared in there. So that's going to become x squared squared plus 4, and then that's all multiplied by 2x. And then x squared squared, remember, if you raise a power to another power, you multiply it. So x to the 4 plus 4 all times 2x, right? And I can distribute the 2x. But I'll just leave it like this. So this is the final answer. And the reason why I want to leave it like this is just to show you guys what happens, right? So when you have an upper bound that's different than just x, what ends up happening is that you're going to need a chain rule every time, right? The format is always going to be this. If there's a number down here, this is going to become a number, and then when you take the derivative, it's going to be 0. But when you take the derivative of this, you're going to need the chain rule. So basically what we could have done was that, okay, right, if you look at the final answer, it's just we plug in x squared into your function. So whatever you have up here, you just plug into whatever functions here. But then, not only that, you have to multiply by the derivative of whatever you plug in, right? So remember, the derivative of x squared was 2x, and that's because of this whole chain rule thing going on in the background, right? So the chain rule says you do the derivative of the outside and plug in the inside. Well, here, if we do the derivative of the outside, that's going to cancel out the antiderivative, and we keep the inside the same. So that just means we plug this in. There's more examples on Canvas, so look at textbook notes 1.3 extra examples for more examples similar to this. So this is all like using FTC part 1. All right, thank you guys. Catch you in the next one.